So in this video, we're going to be looking at how you take the integral with the bounds -5 to -7 of and we're taking the integral of 2 over y to the 4th, and then we have a little square root term there where it's y squared minus 25, and that's with respect to y. So when I look at this problem, I need to ask myself, is this trig sub? Is this some sort of weird, I don't know, improper integral thing? You know, I'm just thinking of all the things that I could do. I can't do a u sub. I can't do just a basic integration table. But what sticks out to me is I notice that there's this square root term here. And whenever I see a square root term, I think of trig sub. And trig sub basically says we can use this term to find out what y is as a trigonometric function. And we can use some of our trig solving strategies to solve for this integral. So let's go ahead and do that here. Let's break down what this actually is saying. Y squared minus 25 is what we're really interested in. Take a look at it. You kind of notice there's two squares and there's a square root. Hopefully it looks analogous to Pythagorean's theorem. A squared plus b squared equals c squared. And if we want to find c by itself, we just have to take the square root. So c is equal to the square root of a squared plus b squared. Okay, but notice here it's a little bit different. We have a similar analogous thing where a would be y, b would be 25 or 5 squared. There's something weird here though. Notice that this is minus, this is plus. That means there's something else going on, and you have to notice here that it's actually hypotenuse minus one of the legs of a triangle. So we're actually solving for a here. This would be equal to a, and I'm going to prove why. So a squared, and we're going to subtract the b over, equals c squared minus b squared. And then to get a, we just take the square root, c minus b, and those quantities individually squared. Notice here we have a completely analogous equation, right? So if we have a triangle here, and we have this angle theta, notice that y is representing the hypotenuse here. So that means that this y term is the hypotenuse, and originally it's just y. So this we know is going to be our hypotenuse. 25 is one of the legs. Now, when we do trigonometric substitution, remember that we need to get it to be y over some variable a. Right, so if the only way we can do this here with it being a leg is I'm gonna do it the wrong way and explain why it's wrong, but then I'll put it in the correct way. 25 is one of the legs. Let's say the leg goes here, okay? And now let's say on the bottom that, and to solve for b, or sorry, the a term here, which is just one of the legs, this would be a. So a is equal to the square root of y squared minus 25. Okay? So I want you to notice here that I have it in the wrong proportions, okay? If I wanted to take secant, for example, or anything, I want to get y over something, so I have to either use secant or cosecant, right? I could use cosecant, but then I have to deal with a lot of weird problems. But if I use secant, I can get y over this, but I don't want it like that. I want it as such, so I want it like this here, y squared minus 25. This will give me y over 5 with respect to secant. So secant of theta equals y over 5. Right, if I did it the other way, it would be y over the square root of y squared minus 25. You've probably seen the formula before. If you have this scenario, you have to put it equal to secant. Okay, this is kind of that proof behind it of how it equals that. So let's go ahead and set that relationship up again. We're going to say that secant of theta is equal to y over 5. That makes 5 secant of theta equal to y. Okay, So we're gonna, for every y, we're gonna substitute with 5 secant theta. But there's one more thing that we have to do is define dy, because dy, when we change it out for a theta term, is going to be d theta. So d theta, we're taking the integral with respect to theta, so we have to find what dy is and substitute it with d theta. So dy equals, and we just have to take the integral, or sorry, the derivative of this. So we know that if we just take the simple derivative of secant, that will give us secant theta tan theta. Okay, so this dy portion, what it's really going to become is secant theta, and there's a 5 here, don't forget, 5 here. Secant theta tan theta d theta. Okay, so now we're going to do a substitution. I'm going to put that up here. So, and it gets quite lengthy. -5, -7 are our bounds. And you could redefine the bounds, but I'm not one to redefine the bounds. I mean, I do it kind of when I'm at the end and I kind of think like, oh, I want to stop here. So I'm going to define the bounds with respect to this and move on with my life. So, we have 2 over y to the 4th, so this is 5 secant theta to the 4th. And then we have a little square root term here. We're going to say times the square root of y squared, which is 5 secant squared of theta minus 25. Okay, and then we're going to multiply this by dy, because dy would be here, but it's not dy anymore. It's 5 secant tan theta d theta. So we're going to say, and I'm going to actually take it and move it to the top, but I'll simply write it out here first. Secant theta tan theta d theta. I'm going to move this term and I'm going to multiply it in with the 2, right? I don't have to multiply top and bottom just on the top, right? That's a common thing that you can do, and it makes seeing the actual answer to this quite simple. So 2 times 5 is 10 secant theta tan theta, and I can just simply get rid of all this junk out here and make it with respect to theta. Now for my simplifications, I'm going to bring the integral down a step instead of just erasing. So we have that 10 secant of theta tan theta. That's going to stay. But we're going to simplify these. 5 secant theta to the 4th. Well, we need to take 5 to the 4th, and let me grab my calculator here. 5 to the 4th. 5 to the 4th is 625, so we're going to say 625. Secant to the 4th of theta, right, because we're taking the 4th power of secant. We're going to multiply this by the square root, and we're going to simplify this. If this is squared here, I don't know what that was. Don't mind me. 5 squared is 25. Secant squared of theta minus 25. And we're taking the integral with respect to theta. I'm going to do something here that might seem a little weird. I'm going to pull out a 5, or pull out the 25 by adding it, multiplying by 5, because that would be an equivalent thing. Okay, so I'm going to pull out a 5 here, and we're going to be left with the square root of secant squared of theta minus 1. Okay, the reason I did this is because I'm going to notice an identity, but before we get to that, let's actually multiply this in to simplify. So 625 times 5, it's going to turn out that this is 3,125 secant to the 4th theta. Okay, so I'm going to notice here that there's an identity that says that And let me actually grab the actual paper here so I get it completely correct, and then we'll rearrange for it. I'm going to put it in red. So tan squared of theta plus 1 equals secant squared theta. This is called a Pythagorean identity. And basically what we can do is we can say, okay, if I could get tangent by itself, meaning that tangent squared of theta equals secant squared of theta minus 1, notice how this equals this. So I'm just going to substitute what this is equal for, tangent of theta, and I can easily take the square root of that. So I'm going to actually go ahead and do that now. And I'll keep it in red so we can see that we just did that. Tan squared of theta. So we just plug that right in there. Okay, so we have this simplification. There's even another simplification we can do. What is, if we have the square root of x squared, what happens to the square and the square root? Well, they cancel, and you're just left with x. Well, the same is true with this tangent function here. It's squared, we're taking the square root of it. It just cancels out the square. So this is actually going to simplify to tan of theta. Even another simplification we can do. I love how this problem works. It just keeps simplifying stuff. Notice that these tangents, there's a tangent on the top and a tangent on the bottom. We don't have additive terms, so it's not on like all of them. So we can just simply cancel out the tangent of theta. Okay, now this integral is getting really simplified. Notice we have now 10 over 3, and let's see if that actually simplifies. 10 divided by 3, 1, 2, 5. 2, 10 over 3, 1, 2, 5 is equivalent to 2 over 6, 2, 5. So I'm going to substitute that in here. I'm actually going to bring it outside of the integral. So I'm going to say 2 over 6, 2, 5. And now we're left with a really, just a simple problem. Secant of theta over secant to the third of theta. Or sorry, no, secant to the fourth of theta. Right? Yeah, correct. Okay, sorry about that. Secant of theta over secant to the fourth of theta is what we're left with. Notice that, again, kind of like that tan idea, we canceled out one of them. So what this is really going to simplify down to, we get rid of one of the secants. This becomes secant to the third of theta. And we're left with this. Okay? There's another identity you have to know, that cosine of theta is equal to 1 over secant, right? Really how it looks probably on your sheet is secant of theta equals 1 over cosine of theta. Okay, so we can actually use this to substitute the secant, right? So we can say that this is actually cosine to the third of theta, right? Because 1 over secant to the third, that is a extremely weird integral to just do on your own, and unless you looked at what the integral actually was of that, like if you had a cheat sheet, you would have no idea how to take the integral of 1 over secant to the third. However, we can do this pretty simply, and how I want to start this is by pulling out a cosine squared. So I'm going to transform this a little bit. I'm going to expand it by saying, and I'm actually going to grab my new marker here. Cosine squared of theta times cosine of theta. What this allows me to do is use another Pythagorean identity where we say that, and let me just make sure I have this right, sine squared of theta plus cosine squared of theta equals 1. I can simply bring the sign over where cosine squared of theta equals 1 minus sine squared of theta. Okay, so I can just plug in or do a substitution here where I say, okay, that cosine squared, that's going to be actually 1 minus sine squared of theta, cosine of theta. And you're going to be asking yourself, why exactly am I doing all this identities and stuff, right? You want to reduce the power as much as you can, because if I have, for example, cosine to the third of theta, you cannot just easily take the integral of that. If I say take the integral with respect to theta, you couldn't do that without doing the splitting idea. You could maybe do by parts, integration by parts, if you really wanted to. But that's kind of lengthy. Integration by parts is just to show you how you can if you absolutely have to. Here it's not the case, because we're going to notice that we're going to reduce the power. And when you reduce the power to 1, well, that's the integral of cosine to the 1 is just sine, right? And if we have cosine squared, what we need to take the integral is a sine, right? Because the chain rule says we need that. Okay, so pretty simple idea here. But just important to understand why I'm doing these identities. It's kind of the thought process I'm going through. It's like, okay, I need to get this in a form where I can just do a simple substitution. That's kind of the whole point. I'm going to multiply the cosine in. So I'm going to say cosine of theta minus sine squared of theta cosine of theta d theta. Okay? I can split this up, or I can just take the integral of both of them. Both will give you equivalent answers. I know that trying to think what I want to do first. Okay, I'll go ahead and take the integral of cosine first. So cosine of theta, the integral of that, right, is sine of theta. Because when we take the derivative of sine, we get cosine. So this is 2 over 625 sine of theta. And it's evaluated at these points, so when we're going to have to do a little bit of plugging back in, which we'll see in just a second. And this is going to be subtracted by, and this is a simple chain rule here. We took the, and we'll do a u sub, but I can do the u sub in my head, but doesn't mean you can. U equals sine of theta, where du equals cosine of theta, right? Notice how u here is to the second, right? We'll just have to do a simple power rule because this will be u du squared. We're going to do the simple inverse power rule, and we're going to see that it's 1/3 u to the third. Hopefully, if you're at this point in your calculus career, you know how to do simple integration ideas. So this is going to be 1/3 sine to the third of theta, okay? We're evaluating all of this at -5 to -7 of x values, not theta values. You can't just plug in -5, -7 and get an answer. It's just not how it works. Also, I made a mistake here. Notice I forgot to distribute the this part to all of them. So it's really 1/3 times 2 over 625. That's an important note. So this will actually become 2 over 1875 sine to the third of theta d theta. Or sorry, not d theta. Evaluated at -5, -7. Okay, so it's getting a little complex here, but what we're going to do to help evaluate at these x values, and you could have solved for theta using the trigonometric relationship, or you could just simply find what sine of theta is and plug in the x values and then evaluate. So I'm going to actually go ahead and just figure out what theta is and plug it in. Because I actually kind of like keeping... Actually, no, I'll go ahead and do it the long way for those who are doing it the long way. I kind of prefer to do that way. It's more thorough. So remember our triangle here, we said that y was here, 5 was here, and the square root of y squared minus 25 was here. Okay, and theta's here. Sine is sine of theta. We found to be we're going to find to be equal to y squared minus 25 square root over y. Alrighty. So using this idea, I'm going to go ahead and erase the top here. I'll erase this too. We'll keep the top part. We're going to substitute for everywhere we see sine, we're going to put that big fat chunk of mess in there. So we're going to say 2 over 625 square root of y squared minus 25 over y. Okay, that's that first bit there. And then we subtract it by, and this would be 2 over 187.5 multiplied by about quite the problem this is. Usually I'd edit all that out and do that, but I don't really give a shit today, so whatevs. Y squared minus 25 over y, but this quantity is cubed, right, because it's sine to the cube. And we're evaluating this at -5, -7. Now you could go ahead and evaluate it just like this if you really wanted to. I'm going to go ahead and do just another simplification step just to make it a little bit nicer to look at. So yeah, let's go ahead and do that. I'm going to say that this is 2 square root y squared minus 25 over 625y. And I'm going to subtract this by, this is going to be 2 times y squared minus 25 to the 3 over 2. Right, because this is to the 1/2, times it by 3. You add it 3 times to itself, it's going to be to the 3 over 2. And then that's going to be over y cubed. But that quantity times 1,875. And we evaluate this at -5, -7. Okay, so that's my work there. I'm going to go ahead and now evaluate this. It's a lot of calculator work, so if you need to write down anything, take any notes, go on ahead. I'm going to go ahead and calculate what this comes out to. So I'm going to find the upper bound first, b, which is -5. So this is 2 square root of, and it's really important that you get everything right here, because if you don't put it in just right, you'll get the wrong answer. 625y, so this is -5 as well. Subtract 2. All this for like four college credits, guys. It's really wonderful, ain't it? It really makes you happy about your life choices. You know, just plugging a bunch of crap into a calculator all day. So I found it to be 0. Hopefully you concur. If not, I'll have to redo this video and you won't be seeing it. But now let's plug in -7 with where the y's are supposed to be. Okay, and I found this to be -0.00187. I'll round it to that. So the area under the curve for this function between -5 and -7 is going to be, I'll put it in both scientific notation and normal notation, 0.00187 units squared. Or 1.87 times 10 to the -3rd units squared. That was that entire integral there. Holy crap, that was a big pain in the ass. I hope you guys enjoyed. If you did, please drop a like, subscribe, comment if you have any questions. I'd love to answer your questions, and have a wonderful day.